Okay, so this is the lecture 9, second module, bias variance trade-off. So we already talked about the bias variance decomposition, and now I want to show you what does this decomposition even mean for me, right? So again, underfitting, overfitting. So just a bit more visually, underfitting is my model is too rigid. It's have high bias. So theta truth versus the theta bar. Think about bias is my model intrinsically actually very different from the truth. All right. So overfitting. So in fact, this just the variance is too large, but this model is so flexible. In fact, I should be able to fit it, but the variance is just too large. So again, so high variance is a specific theta from a training data, theta I, let me do theta D, minus different from that theta bar. Variance is only about blue points. Remember that. Bias is the red point versus the mean of the blue points. Okay, so now I want to show you this. So what causes or what figures we normally would like to show you is this figure. So, and the previous figure we actually asked you to draw, actually in the homework 2, you're going to draw is just for one training data, you will draw, when you're changing the model complexity, and this can be the k-nearest neighbor k, or regional regression lambda, or the polynomial regression d. What you're going to expect, if on the right is more complex models, you always will see the training error goes down. But your testing error actually have this kind of valley shape, and this valley shape, the low plateau regions are normally the sweet spot of the model you're going to pick. And in fact, what causes the left, we always tell you the left is underfitting, right? The left is underfitting. The right is overfitting. And the right noise is mostly caused by the variance noise, the variance error. The left is mostly caused by the bias error. So this causes, this you can actually tell, it's the expected test error. You can think about this is our EPE. All right. So EPE normally has this kind of valley shape. Remember that. Kind of valley shape when you have the model complexity as x-axis. And two sides are caused by the different kind of error in that summation decomposition. So, and same thing on the classification case. Let's just see what do we mean the variance of my model, right? So let's see the k-nearest neighbor equals to 1 case. So assuming in my training data, I actually do not have this 3 blue points, and then my decision boundary will immediately without that actual region to be predicted as blue. So just a small changes in your training data makes your decision boundary changes a lot. So this is actually means my model is so has high variance. But on the left, if I change, assuming I'm changing some of the blue points, but my decision boundary will not change too much. So this actually means my model is not that it's not that too high variance. Okay, so same thing on these regression cases. If you remove some of the training data here, and your regression immediately changed, and so your model just so sensitive to the training data. So when the model complexity increases, your model variance normally increases. Okay, so again, this curve, so this expected prediction error. So how could I, that's expected prediction error, right? So what should be a nice in the training data, when we performing the workflow, we actually can approximate that. So in fact, cross-validation error, it's a very good approximation to the EPE or ET. Let's just call that EPE. We can also call that expected testing error. So there's actually a proof in the extra slides. There are proofs proving cross-validation error a good approximation of expected prediction error. So I told you this bias variance trade-off, right? So on the left, it's mostly the expected prediction error. It's dominated by bias error. On the right, it's dominated by the variance error. So you need to figure out the sweet spot. And this is a curve normally called a validation curve or learning curve. You always want to plot this curve, to do model selection. And this is the homework in all of the different kind of regression models you need to implement. You need to draw this curve. Okay, so I think next one is training error can always be reduced and when increasing the model complexity. And I already told this, so it's very clear. So when k-nearest neighbor k to so small k equal to 1, think about in k-nearest neighbor kn training error, in fact, is close to 0. In the polynomial cases, you can also increase the d a lot. You can also get training error, feed the training data just perfectly. Your training error always decrease when your model becomes more complex. But the variance of that model kind of increase, so which means the generalization not necessarily improved. So I think this page kind of repeat what I see. So again, so very important to realize what do we mean model more complex for different kind of models. More complex, and then less complex, more rigid. So we actually told you the k, in the k-nearest neighbor, k decreases, means more complex. D increases, which means more complex. In the regression model, lambda decreases, which means more complex. This is the regression model. So I think this can hopefully become an instinct. No, you don't need to just refer to that method again, but whenever you see this, you already understand how the hyperparameter related to the complexity, and you know what's the right and left, and to look at this kind of curves. Oh no, I should do not lambda increase, but actually lambda decrease. So lambda, when lambda equal to 0, that's actually your original model, right? Okay, so now I also want to emphasize you have to also consider in your data, in your workflow, so your testing data also has randomness. And this testing data randomness, it's actually pretty tricky. So a lot of state of the art, they claiming they're really, really good, but in fact, they overfit their testing data. They're just the best on that testing specific D test. But it's not necessarily the best to the expectation of the D test. So it doesn't generalize to all the possible testing cases. So this is a very important critical point you need to keep in mind. So this page actually trying to show you when you have different testing data. This is a ridge regression model. We know the new model. We just create all different kind of training data, all different kind of testing data. And because we know the truth, right, we actually can plot you the bias, the theta. We know the truth, right? We also know the theta bar. We can just randomly sample many training, and we get it. And we also, by that way, we can also plot the theta hat versus the theta bar and the variance, the expectation. Then you can plot this curve. So bias quadratic plus the variance, in fact, is this this purple curve. This purple curve you in this case, because you know the truth, so that's why you know the test error. So you can actually tell, because bias and variance summation is the EPE, right? This is what we actually did equation-wise. It's an equation, it's just the definition. And we can actually tell test error, the observed test error, cross-validation test error, almost follows the same shape as bias plus the variance. So this is actually trying to show you cross-validation error, or in this large cases, the test error, when you have enough good coverage of the population. Again, is that joint probability. Do I cover my joint probability population well? If I can cover that well, my test error is a very good approximation to this true generalization error. Yeah, but in fact, in the real cases, you actually do not know theta because we don't know the truth, right? How do I know the truth? Okay, so theta, so it's truth, right? We don't know it, it's unknown. So we actually cannot plot you the bias and the variance. What we can only get is the test error. So that's why we use this test observed empirical test error to guide us to model selection. All right, so I hope you start to understand the logic, why that it's a good thing. Why we are using this pretend test cases and to guide us for generalization. So there's theoretically you actually can do this, also prove this. We can prove, so we actually can prove we actually can prove cross-validation is cross-validation error is a good approximation of generalization error. All right. Okay, so enough of this. There's also some extra thing about in the cross-validation. How do you pick K? I don't want to cover that. There are extra slides talk about it. Picking the K, it's actually pretty tricky when your data is small. When you have smaller data, picking the right K, it's relevant to this variance of your estimation. But let's skip. Okay, so now the bias and variance trade-off is model with too few parameters are inaccurate because of large bias or too rigid. Model with too many parameters are inaccurate because of a large variance and just too sensitive to the sample randomness. So we show you in this case again, so the left side is low variance, high bias, and right side is low bias, high variance. A classification, left side low variance, high bias, on the right side is low bias, high variance. So this case is almost the smallest bias that is possible. And the model complexity is super high. Okay, so I will use a few seconds just tell you, after I learned of all this, so what? I just know, I'm still just plot my hyperparameter versus the testing loss and training loss curve. It's the same thing as we did before this class, right? So how do this bias variance trade-off actually guide me? It actually can help you to guide you to remedy in the cases when you know you underfit or when you know you overfit. So which means what? So first, you need to figure out, are you overfitting or are you underfitting? Okay, yeah. So how do you know you're overfitting or underfitting? So very simple strategy, like we always say, high, when you observe high training error and also high test error, you are in the underfitting. Your issue is underfitting. When you have high test error but really low training error, you actually know you're in this regime of high variance. So yeah, so this is high bias, high variance. So first know where you are in this complexity regime and then act accordingly. What I meant accordingly is, so in the left, you solve the bias issue. On the right, you solve the variance issue. Okay, so again, I emphasize many times, bias is about inaccurate rigid model, too simplified. Variance means too, your model is too sensitive, maybe too flexible. Yeah, all right, so a little bit too slow, but I will cover this really important last section in the next Thursday class. Thank you.